Okay. So first of all, I have to apologize for my Australian accent. It's like really hard for me to fix it. So hi everyone. So should I start it?
Yes.
Please.
No, we can.
Okay. Hi, this is Tiger Lu, and our group is doing the affinity element analysis and simulation of the failure for the Tacoma Narrow Bridge. So I will do the background part and the methodology part, and Henry will actually do the Henry and David will focus on the modeling and of course harmonic analysis and model analysis. And finally, Andrew will do the result gathering part and the conclusion. And of course, the contribution. Yeah. So the background. With the continuous development of the modern society, suspension bridge were constructed widely due to its characteristic of holding longer span. As we know, a longer span always better. Yeah, because it holds a horizontal clearances and it looks better. Yeah. Okay, so this is the Tacoma Bridge. The Tacoma Bridge was was constructed in 1940, and it is a typical example of a suspension bridge. And this is the dimension of the bridge. The total height from for the column is around 60.35 meters, with the width of approximating 12 meters. And the total length of the bridge is around 1810 meters, and the main span from two columns is around 853 meters. That's the basic dimension. Of course, the radius for the main span is 0.35 meters, while the secondary, which is the perpendicular cables, the radius is 0.15 meters. However, it failed and collapsed due to the aeroelastic flutter. The failure of the Tacoma Bridge has become a famous case for the bridge engineering study and structural dynamics course nowadays. It's due to the torsional oscillation caused by the wind at the velocity around 67 kilometers per hour. As a resonance occurred when the torsional oscillation met the natural frequency of the Tacoma Bridge. In fact, the resonance induced by external forces might happen at all similar suspension bridge. So that's why we choose Tacoma Bridge as a typical example. Oh. Yeah. So for the main objective of this research, a detailed determination of the natural vibration frequency for all Tacoma Bridge by applying finity element method is discussed. ANSYS will be mainly used to perform the FEM, which is finity element method, calculation to determine the natural frequency of the old Tacoma Bridge. Of course, a comparison between the final estimation from the model analysis and harmonic analysis of ANSYS and the experimental value will be conducted and shown. Yeah. This research can help engineers to solve related problems and use it to be like a simple guidelines when designing a suspension bridge to sufficiently avoid the phenomena of resonance. and hence prevent from collapse. Yeah. So for our methodology, we use analytical method and numerical method. So for analytical method, which is like hand calculations, the advantage is it has a high accuracy. The accuracy of the solution is relatively high, and it clearly demonstrates the relationship among variables. However, it's really hard to find appropriate analytical method for a specific object, such as a suspension bridge. In this case, in our case. Also, nonlinear differential equations is really hard to solve for student, and yeah. And for numerical method, of course, we use ANSYS as a finity element method. The advantage of numerical method is convenient. It has a higher efficiency, and it also simplifies the calculation of natural frequency. However, like it's really just an estimation, and it has a relatively lower accuracy than the analytical solutions. So analytical wise, the determination of the natural vibration frequency of a real-world suspension bridge has been regarded as a very complex work. Instead of using analytical method, the numerical method such as FEM was considered as a higher efficiency approach to estimate the natural vibration frequency than the traditional analytical method, like I just talked about before. And the finity element analysis was one of the most critical developments in applied mechanics. And FEM replaced the governance differential equations for a distributed mass system with a system of linear equations. This also shows how FEM simplifies the calculation of natural vibration frequency. And now that's the comparison of the result between numerical and analytical method. So as you guys can see on the table here, the result from harmonic analysis suggests that the most critical natural frequency was around 0.15 Hertz, while the analytical result of natural frequency, which was calculated by Professor Farquharson, it's around 0.21 Hertz, which is slightly lower than the observed data from the analytical solutions, the numerical result. And of course, Andrew will talk about the error analysis at the very end. So now it's Henry's turn to introduce the actual modeling process.
So Professor, can you hear me? Yeah, should I go?
I can hear you.
Yeah, okay, I got it. So hello, it's my thanks for Tiger's presentation. It's my honor to show my part. So let's go it. So first, my task is to create the model of Tacoma narrow bridge, and I will show some detailed information. So this is just an overview diagram, and the steps on the screen is the sequence about how to create the model. First, we just build the bridge deck, and the length of the deck is 1,650 meters, and the length of the width of the Tacoma Bridge is 12 meters, and the thickness of the Tacoma Bridge is 2.4 meters, and they will just build the beams. And the part of the up part of the beam is 60.35 meters, and down part of the beam is 60 meters. And they will just build the bridge piers and the main cables and second cables. So these are 3 view drawings, and the first one is frontal view. And the second one is side view. The last one is just a top view. So it's just our model. So through discussion, through group discussion, we just need to decide use 3 systems to analyze the model, and which is just the model, harmonic, and fluent system coupling. And I will show you the first 2 methods, and David will show the third method. So as we can see, this is our model cloud chart, and this is our deformation. So as we can see, the lighter the color and the greater the deformation. And I think, in my opinion, the model system is a desirable way to help us to get the natural frequency. And this is the results. This is the results. So then I will show some typical animations. So the first one is just the model 1, which natural frequency is 0.11 Hertz. And I will show it. So you can see the deformation is just up and down. So, but this result is not what we want. And this model is just about model 3, which frequency is 0.15 Hertz. As we can see, there is some little torsion on the bridge. So I will show the magnified pictures. Yeah, this is just a torsion. So I think it looks a little like the a little like the bridge collapsed. So then I just did harmonic analysis. It's also. So I will show the pictures. So something interesting. This picture is just like what we did about model 3. So I think maybe my result is reasonable. Our result is reasonable. So this is also a magnified pictures. Then I will show there are 2 charts about my our results. This is frequency response 1, and you can see the critical point is just at 0.15 Hertz, and it's amazing. So the down part of the chart is just a rotation angle, and it's just 0 and 180. So this is a frequency response 2, and so you will find something interesting. There is a critical point, and here is another critical point, and but I will, because of the time, I will not make the detailed explanation, and my group member will explain it in the final part. So next, David will show the fluid solid coupling, and let's welcome David.
Okay. Okay, for this part, we just use software fluent in the access mode. It's a one kind of access mode to input the wind velocity around 90 meters per second to the horizontal. You can see the horizontal section of the bridge, and the direction of the wind. The direction of the wind that we have simulated on the answers is exactly the same as the wind. Hi, sir. Can you hear me now?
Okay.
Okay. Okay, so for this part, we just use software instead. For this part, we just use software fluent in the ANSYS workbench to simulate the wind to apply it on the horizontal section of the bridge around 90 meters per second, and which exactly the direction of the wind that occurs that makes the bridge collapse at the time. And you can see the phenomenal resonance here. And even though the reason of the bridge collapse is not simply caused by the vortex vibration, the up and down vibration, and it can only do some damage to the failure life of the bridge. So we just create an ideal model for analysis. And you can see from this video that since the frequency of the wind is approximately the same as the frequency of the bridge, and so the resonance occurred, the phenomenon occurred, and you can see this part. And for the definition of the resonance, it's just basically a physical system that vibrates at a great amplitude than other frequencies at a specific frequency. Or you can express in a simple way the superposition that we have learned in high school. And we can see the color map on the right-hand side. It's a picture of our total deformation, where we set the 6 surfaces and the bridge pier is fixed, and then we apply the surfaces except the 6 as the intersurface between the fluid and the solid. That the wind would have a direct influence on the bridge structure. It was looks like our set a boundary condition of the wind load, and in the animation, the bridges looks like the vibrates up and down, and it really looks like a sine function because the bridge itself has experienced a periodic aerodynamic force on it, which so we can see from this map here, the red area is where the deformation is the largest and somewhere near the middle part. So when you compare it with the real image, it can show our simulation is nearly correct for this part. Okay, and for the wind velocity diagram, you can have a clear observation of how wind has changed during this time of 5 seconds that we have simulated before. And you can see the green area is the area where the eddy current disturbance, which makes the vibration. It's a vortexes, and you can see from these pictures in different planes. Furthermore, we have extended our research and have done some evaluation on how to improve the bridge stabilities. And you can see you can see the up and down vibrations are basically caused by the dominant vortex A on the upper side and the dominant vortex B on the lower side of the bridge, which causes to vibrate up and down. For the solution, the spoiler is just basically like a horizontal wind plate structure that we usually store it on the railing of the bridge. And our aim is to destroy these double vortex modes. As you can see, the dominant vortex A on the upper surface and dominant vortex B on the lower side. So we have to destroy it to make the bridge to not affected by this vibration mostly. So the flow field distribution of steel box girder is significantly changed by the spoiler. It is due to the separation of the airflow behind the spoiler and the vortex shedding. And you can see from the diagram, the moving path of the airflow is changed. And now the airflow is moving a horizontal path of its process, which causes the dominant vortex on the upper surface destroyed, and which means this mode does not exist. And this comes to an end to the vortex vibration. So for the next part, Andrew will give us some summary on our project. So welcome, Andrew.
Thank you, David. Okay, can you hear me, Professor? Okay, oh, cool.
Yes.
Thank you, David. So far, we have done some model analysis and harmonic motion analysis already. So let's just move on to the result discussion part. The result discussion part consists of two components: the model analysis results and the result of the harmonic motion analysis. Hold on. Sorry. Yeah. So the first part I'm going to talk about is the model analysis. So this table on the left-hand side was the model analysis value of the natural vibration frequency. I just highlighted in the yellow column, and the table on the right-hand side, which is the second part, is the calculated natural vibration frequency from the Professor Falk-Hansen in 1949, and I also indicated in yellow color. So to verify the validity of our model, we gonna use some tools like linear regression to see how our results looks like and how they are performing compared to the real one. So the graph on the right-hand side was the linear regression graph, where the orange color represents the calculated value and the blue color represents the model analysis value. So you guys can see the R square there. Oh, sorry about it. So the R square on the table represents the linearity. So the higher R square value you have, the better linearity you have for this set of data. So they both perform a really good R square in this time. So we can just say those two sets of data are linear. The logic behind the linear regression is to determine. Wait, what? Sorry about it. So the logic behind the linear regression is to demonstrate the linearity of your data. If your data is performing a really good linearity, that means your data, your future data is predictable and it's logical. You can just basically say, so from the pattern, we can just say our model is really similar to the real model, or either way, we can just say our result from our model analysis is really close to the calculated model because they both performing a really good, linearity, and they are predictable, and they have a really similar pattern, and as we can see from the graph. So that means we have a good estimation so far for the natural vibration frequency. So let's jump to the harmonic analysis part. So the harmonic motion analysis is achieved by adding some loads or external forces to your mode, and see where is a local maximum amplitude occurred. You guys can see from the table. So that means if you find the local maximum amplitudes and its corresponding frequency is where the natural resonance occurred in the real life. Just in this case, the observed frequency was the 0.15 hertz and 0.4 hertz, whereas the real data from the Professor Farquhar Hansen was 0.2 hertz and 0.6 hertz. I'm going to talk about this later. So basically, our results are really similar to the real one as well. So I'm going to talk about the discrepancy this time because we are just the normal human, and we fight against the elimination of the error for 1,000 years. But nowadays, we just realized to totally eliminate the error is an impossible thing. So what we can do just to reduce or to minimize the errors. So there are 3 approaches for us could be used to minimize the error. The first way we could do is to find out more details about the Tacoma narrow bridges. So for example, if we can find a proper drawing or a really detailed drawing about the Tacoma narrow bridges this time, we can just make a better we just have a better modeling, and we can just make our model much preciser. And the second thing we could do is to increase the mesh numbers. In this case, we are using the student version of ANSYS. That means we have a really limited mesh numbers to do the finite element method. So the finite element method is just an approximation based on the number of segments you have this time. So if we have a large number of mesh numbers, and we could have a much accurate result, I believe. So the second thing is to improve the parameters and improve qualities. For example, the wind load is the main external force for our bridges, the side view wind load. But to get a value of the wind load, it's quite complicated, and you have to think about the real world. Like the Tacoma narrow bridge was located at Seattle, so that means we have to know about the temperature at Seattle in 1949 in November, and we have to know about the pressure status, like is it one bar of standard pressures or not, or something like that, to get a exact value of the wind load. In conclusion, we can just, based on everything we have done so far, we can just confidently say the numerical method, which is the finite element method by ANSYS, is a more practical method than using the analytical one. Especially for some specific cases like us, because we are just easily performing the software and we got the expected result at least. In the real life application, we can just simply use the finite element method to simulate, to do some similar estimations like the natural frequency estimations in the real world to prevent some destructive resonance for the suspension bridges. This is kind of like a real world applications we could do, and this is actually based on what we have done for the simulation of Tacoma Narrow Bridge this time. So let's move on to the contribution part. So we basically working in pair. So me and Tiger just responsible for the report writing and the literature review, this kind of writing part. And Bofan, Richard Henry, and David, they are responsible for the model creating and the performing and model creating some answers, some real technical parts. But we do have some good interaction between each other. For example, me and Bofan also do some simple estimation about the model analysis and harmonic analysis. Yeah, we do have some interaction between each other. So it's not completely we just do the certain part. We do have some we do have do some side thing to help each other. So this is the reference list. This is all the information we are getting from. Yeah. So thank you for the Professor Boha for giving us some theoretical advices and teach us the things about finite element method. And I want to also thank I want to give my thanks to TAs, Curtis as Blair. They helped us a lot about modeling and the software. And I also want to thank all my brothers, all my classmates I've met. And yeah, that's a really good experience I have had. Thank you.